Sure. So yeah, so good afternoon, everyone. So first, I would like to deeply thank the organizer, Serguei and Natacha, for setting up such a wonderful event. So as you can see, my talk will be about ultrafast spectroscopy of Coherent Phonon across the mode transition in materials, right? So maybe I'm going to skip this pump probe explanation because you're all kind of quite familiar with this. And I will not deeply skip that one, but you heard a tiny bit about the mode transition. So in a nutshell, it's the competition between the electronic bandwidth W and the on-site repulsion U. This is really oversimplified, but this is the picture we'll keep. And so in our case, we are quite old-fashioned. The tuning parameter we'll be using to do this mode transition is just hydrostatic pressure, as it's done quite common and quite often. So the sample we're interested in, you already heard about this one, is a vanadium sexquioxide, V2O3, with the given phase diagram, which is quite famous. So if you're with pure V2O3, chemically speaking, you're on this dashed line. So at room temperature, you're in the paramagnetic metallic phase. If you cool down, you have a magnetically ordered phase, AFI, but we'll not discuss that one. And what is known is that if you do chromium substitution, basically you push the system into the paramagnetic insulating phase, And so what you can do once you're in this paramagnetic insulating phase is just applying pressure and you go back. You do the true mode transition, which is isostructural, no symmetry breaking. You have a large volume change in the case of the V2O3. And this is first order, meaning that you have hysteresis and coexistence, right? So this is what we will be looking at, this mode transition. Okay. So one idea is that, of course, if you want to investigate this, you can do transport measurement, or you can do diffraction, but this might be kind of tedious in our case, under pressure. So one point where we're thinking about is what are the structural signature of this mode transition with large volume change. So basically, here you have Raman spectrum of the pure V2O3 in blue, which is basically the metallic phase, and in the chromium doped one, which is basically Pi under ambient pressure. And what you can see is that there is, so I have to go the proper way, there is a red shift of frequency if you go from the insulating one to the metallic one, meaning that you have lower frequency, right? You can see this for the two A1G modes and the EG ones too. So it seems that just based on that observation, you can use, you can use Raman spectroscopy, or let's say if you're able to measure optical phonon, you can use this as the signature of the non-symmetry breaking mode transition in V2O3. So first, what the people in Nantes have done, our colleagues that are working on this sample, it's that they've used the classical V2O3 and also the chromium doped. They've put this chromium doped sample into, here you see this diamond anvil cell, and you apply pressure and you expect to, wrong button again. You expect to cross the phase transition. So let me guide you through this. So in this deep blue, this is the ambient pressure one, so with a frequency of 2050 wave number for the A1G1. And as you apply pressure, you see this kind of red shift. And after you end up with this 2030 roughly wave number for the A1G mode at 1.7 gigapascal. So what is kind of straightforward, so this is this one in blue, this is the chromium dope, which is Pi insulating. In brown, this is the pure V2O3, which is metallic. And you see that once you're applying pressure, you have this compressed chromium, which is supposed to be the PM, that is showing kind of the same frequency with some slight difference. So this is a clear indication that we should be able, if we can measure the A1G mode, we can be able to make the monitoring of this mode transition, right? So you can go slightly more into detail. So again, this is the diamond anvil cell. You have the unpressured, so this is supposed to be the insulating one, the metallic one. And you can also do the monitoring of the observed A1G mode. So what you can see is that you have a small softening of these modes pre-transition. When you approach the transition, then you have a sudden drop, which is the marker of this phase transition, and then you have a plateau, which is kind of indicating that you're in the metallic phase. still, something you have to keep in mind compared to what we are doing, we are in the single crystal chromium doped materials, right? So of course you heard already a tiny bit about Coherent Phonon spectroscopy, and indeed this is another way to access A1G modes in materials, but this time in strongly out of equilibrium case and in the time domain. So this is really oversimplified the way I describe this, so I apologize, but in a nutshell, what you will observe if you have this kind of phenomenon is a modulation of the dielectric function of or the diffraction pattern at the optical phonon frequency. And if you're really lazy and you just want to do the simplest analysis you can do, you will consider that you could fit this with a damped, exponentially damped oscillating function, so cosine, and you can extract, in principle, frequency, damping, and the phase. So back in the days when this was observed for the first time, there were like two mechanisms to describe the optical phonon: the displacive excitation of Coherent Phonon and the impulsive Raman scattering. Turns out that through this publication from Merlin that you can unify everything through the Raman formalism. But what you have to keep in mind is that when you do this really simple analysis, optically speaking, what you will be mostly sensitive is zone center optical phonon of A1G character, right? So then we in V203, in fact, it was known for several decades that there were current optical phonon. So this was performed in '98, I think. So they were using, in this case, if you're familiar, they were using a femtosecond oscillator, meaning that you're using nanojoule. So it's really low excitation, but still you get this kind of classical trend. You have the strong electronic peak at time 0 and some wiggling. So you can either plot the derivative or you straightforward, you do the Fourier transform. And what they were observing back in the days was this nice single frequency oscillation, which was matching 7.4, matching quite well the zone center A1G mode. And because you're in the metallic phase, you're doing a genuine electronic excitation, so it's more like the DECP kind of mechanism, right? So then in our case, the sample is a polycrystalline thin film grown substrate. Still, you can do the same kind of pump probe measurement, so a nanometric thin film of 200 nanometer thickness. So you're in the metallic phase, you do the pump probe experiment, and you see nicely that you have this beating, so this oscillation of the optical property. Then you do the Fourier transform, and what you got, which is this 7.1 terahertz, matching everything that was done previously. So far, so good. So we're on the good path. So then still something which I will not say is peculiar, but it's not always that common. So people are kind of used to have a dependency of the phonon frequency over the excitation density. Like the most famous case is the bismuth one. But in the case of V203, and this is really interesting for us, if you crank up the fluence to really high excitation density, you see exactly nothing occurring regarding the phonon frequency. Meaning that the electronic temperature is not a parameter that will change or tune the phonon frequency or the lattice potential in that case. And the same is also relevant for the damping time. So still, but this is in agreement with everything that was done so far. So now we move to the core of our experiment that is doing the very same kind of experiment, but in this case with our pressure cell. So this is a Holstein pressure cell, if I can say. So this is nothing that has to do with anvil cell. It's helium-based, so it's just we use a compressed gas and we push onto the sample. And basically our operated scheme is between 0 and 7 kilobars, so 0 to 0.7 gigapascal if you want. And so what we have done is perform spectrally and time resolve experiment with below 100 femtosecond time resolution. Okay, so first we'll start again with the simple, let's say, V203 case. So as it was grown and as I showed you previously. So something you have to keep in mind is we do not expect any phase transition or anything fancy when applying pressure. We're just going more deeper into the metallic phase, right? And so this is what we have obtained for the phonon frequency. So basically, you see this value of 7.1, let's say, or 2, which is in agreement with everything done so far. But still also, on contrary to the excitation density, let's say, control parameter, you see that there is a small hardening of the A1G frequency, which is already telling you something fancy, is that in some sense, the system is more reacting to the pressure than to the photoexcitation. right? But as I put in my title, the target we have is to do the mode transition, right? So how we can achieve such a thing? So thanks to our colleague, you can have, let's call this a strain V2O3 sample. So the idea is that you have some thermal expansion mismatch between a substrate and a thin film, and this will induce some strain that will push, even if you're chemically pure, this will push the system into the PI phase at room temperature. So how can we be sure about that? Is basically if you record the evolution of the resistivity over temperature, you see a double hysteresis, meaning that you cross two transition lines, which means that you start from PI, you go into PM, and then from PM you go to AFI, right? And based on those two transition temperature, we can expect that, let's call the critical pressure to cross the first order transition line to be between 2 and 4 kilobars, which is basically the range of our apparatus. So this is quite nice. Okay. So then this is the kind of, I show you really raw data, the data you collect when you're doing an experiment on the flight. So this is the transient change of reflectivity following the classical 800 nanometer pump excitation. So you see that you have a big component, which is here around time 0. And then I hope you can see you have all this wiggling, a small signal lasting for 1 picosecond. And those basically are, from one hand, the very first signal is this, it's an optical nonlinear contribution from the sapphire window. That basically it's not playing any role in what we're interested. And the second one is this optical phonon, modulating the full spectrum. Then you can sort out and look at a single wavelength kind of dynamics. So this is what you obtain. So if you see on that one, this is around 670 nanometers. So you have this strong nonlinear signal, and then the optical reflectivity wiggling for a picosecond. So I hope that you can trust me that we can easily extract frequency and damping with such a data quality. And if you push further, you can even do the full fit of the time trace, meaning that you have the nonlinear optical component, the Coherent Phonon with frequency and damping, and some kind of additional affine function which is dealing with the thermoelastic response. Still, if you remember, I told you that normally we should be able to extract frequency, damping, and phase. Still, the drawback of our experiment is that we have what I show here in red, this nonlinear contribution from the optical window. And basically, this generates some kind of entanglement between the first electronic response of the V2O3 and the nonlinear response from the optical window. So it means that in some case, in some sense, we're losing the sensitivity to the electronic response. But as you can see, it's still more than enough to get the phonon frequency and damping time, right? So now the key drawing, let's say, or the key results. So this is the evolution of the phonon frequency over pressure for our strain V2O3. So we start at 1 bar, let's say. We have 7.5 terahertz, which is nicely matching what we have observed for the insulating phase in chromium doped. Then it's linearly decreasing up to 3 kilobar, reaching the lowest value of 7 terahertz. Then it's increasing a tiny bit up to 4 kilobars. And after you have a plateau-like response over pressure above 4 kilobars. So for the damping, it seems nothing really is correlated with the pressure itself. So it's kind of slightly noisy, let's say. But still something we can think of based first on the thermal resistivity and our experiment is that this plateau-like is the occurrence of the PM phase, and so that we indeed perform the mode transition in this case, right? So then we can put together the unstrained V2O3, which is purely metallic, and the strained wine, which is supposed to undergo the insulator to metal transition. And so what you kind of look is that indeed, if you extrapolate the linear dependency for those two, the unstrained, so purely metallic one, and what we expect to be the metallic phase, there is a kind of a global agreement. Still, something you may notice is that for the values around 3 kilobars, it's much lower than the simple extrapolation of the metallic phase frequency. So it means that a simple model considering only a two-phase system, with two values of phonon frequency is not enough to explain our observation. So yeah, we're struggling a tiny bit to get a model, and then we came across, or basically Etienne remember, in fact, this model developed by Antoine Georges back in the days, which is the compressible Hubbard model. So the idea is the following, is that you compute the free energy of the system considering the electronic contribution, which is a half-filled band in the Mott-Hubbard classical fashion. And then you do this development around a reference volume, V0, which is embedded the pressure and the elastic bulk modulus. And what they did what they did observe is that basically what is plotted here is the evolution of the sound velocity in function of pressure, when you cross this Mott transition. And as you can see, you have this kind of pronounced softening. Then it's increasing again, and you reach something which is somehow similar to a plateau-like or a really weak dependency. And it's really, really reminiscent of what we have observed, for our A1G phonon. So what they quote, which is kind of interesting, is that close to the Mott transition, lattice degrees of freedom react to the softening of electronic degrees of freedom. This results in a change of lattice spacing, diverging compressibility, and more important, critical anomaly of the sound velocity. So still, I have to remind you that in our case, it's slightly different because what we're probing is not directly the sound velocity, but this is the frequency of the A1G mode probed through the Coherent Phonon mechanism. Nevertheless, there is still good similarities, let's say. So if I kind of try to put the two together, so on that side you see the prediction made by Antoine Georges and co-workers. In blue, this is the Raman measurement obtained with the diamond anvil cell. And here what we observe is that similar behavior, but in this case probe in ultra-fast fashion in the out of equilibrium dynamics, Okay, and still, yeah. The key point is that you cannot explain those 3 points if you're not considering lattice degrees of freedom close to the Mott transition, right? This is So just to sum up, basically, so we have a good agreement between the static Raman spectroscopy and the Coherent Phonon spectroscopy. I hope that you do believe that we have a strong indication of the pressure-induced Mott transition in our case. And I think the most important message for me is that really in those kind of samples, you really have to go beyond the Mott-Hubbard model near the first order transition line to explain all the physics at play, right? And to conclude, so I will thank all my collaborators. So Thomas Gauthier was the PhD student doing most of the job, and all my colleagues from Nantes, including Etienne, which is sitting in the audience. And I thank you for your attention.